students, activists, coming from different political perspectives, but we all share a common respect for the work of Karl Marx and a belief that his work will remain as important for the future as it has been for the past. And we have a number of excellent speakers lined up for us, but today we're especially lucky in having Sandeep here to discuss climate change and the renewable energy revolution. So here to introduce Sandeep is his comrade and countryman.
You are also my countryman. This is my country.
Anyway, it's all yours. And we'll go for roughly an hour and then switch to Q&A. Comments.
Comrade Gene, we are internationalists. Workers have no country.
Say again?
We're communists. Workers have no country. So therefore, the whole world is our world.
I'm a free-born American citizen.
Okay. All right. It's a pleasure for me.
Pay taxes to the Imperium, isn't that great?
It's a pleasure for me to introduce Sandeep Agarwal, who has a PhD from the institute that I went to. So our alma mater is the same. They gave us excellent technical education, and we were both had a same mentor in political education, A.P. Shukla. And Sandeep actually was a founder of a workers' organization at the campus fighting for the most exploited and oppressed, the Dalits workers on the campus. And so he's a founder member of that, with which I'm working to this day. And whenever I go to India, I sit with them. Sandeep also worked for several years in what is known as Mumbai now, Bombay before, among the workers, organizing the workers. So he has been an organizer, and he's been a founder of Workers' Support Group, and but he also is very highly educated, has a PhD, and he knows the subject of solar energy, renewable energy, and has worked in that field for the past 20 years. So it is really my pleasure and honor to have Sandeep present today. Sandeep?
Should we get started or wait for another?
I think we can get started because people who are late should
and is
pay
this
for
working,
it.
Raj? It doesn't seem to be working. In case you're recording, this may
Can
not.
I just jump in for
is not
one
on.
minute, Raj?
Okay, all right.
Before we get started, let me just say that this is a topic of great interest, both climate change and the energy revolution. And we gave a talk several weeks ago called Lies and the Liars That Make Nuclear Weapons. And then we had David Walters, who's on the other side, not in favor of nuclear weapons, but in favor of nuclear power. And he gave a complimentary talk, and maybe at some point we can bring him, and he had a comrade with him, that shared his rather bizarre views. And
Well, they're not in CNN.
well, anyway,
They're gonna be bizarre.
it would be good to have them back with Sandeep. For
Yes,
maybe
their
a round
claim,
table or something
Sandeep,
like
was that solar power is not a viable alternative.
Sure.
Okay.
Sure.
So with that, I think maybe you can start, and those who come late pay for it by being late.
Okay. Thanks, Raj, and thanks everyone for coming here. Now, Gene, I would not be talking much about nuclear power, but I believe that nuclear power has a small role, but not a very significant role in the world as it is unfolding today. But I'm not anti-nuclear, but I am very, very cautious about using nuclear because the implications of nuclear meltdowns can be very severe. But more importantly, I believe that other sources of energy are far more effective than nuclear, and I would only briefly touch upon the nuclear issue. So if we follow the media today, these are really confusing times for us. On the one hand, we keep on reading about how forest fires are engulfing the world, globe is warming, we talk about heat waves, Arctic melting, all kinds of things happening to the cryosphere, all the ice, the ice world around us. Oceans are rising, oceans are acidifying. So it really sounds very, very dystopian, when you look at what's happening to the world with global warming. This is one narrative that we hear very often, and last couple of days there has been so much alarmism about Amazon and how farmers are cutting down and burning Amazon to grow soy there. The other narrative that we hear very often is one about renewable energy, and there is so much triumphalism there, that hey, solar and wind are going to dominate the world, and electric vehicles are going to replace all the internal combustion engines very soon. And it sounds like very, very triumphalist, as if renewable energy is going to solve all world problems or world energy problems. And the third narrative that we hear very often is how Asia, led by China and India, but now not just China and India, but Bangladesh and Vietnam and rest of Southeast Asia, how people are getting pulled out of poverty in a big way, and how extreme poverty is ending in Asia, and 1 billion people have already been lifted out of poverty. But all this has happened on the back of fossil fuel. This infrastructure has not been built on renewables. So if you put all these three narratives together, there are two sort of burning questions, or I would say just one burning question that is very topical for us today, and which is our future utopian, where we would be able to build a world based on renewable infrastructure with enough resources to provide 8.5 billion people of this world the same living standard as middle class of the developed world has? Or are we really looking at a dystopian future where the world is resource limited, we are consuming too much, things are coming to an end, and the world driven by capitalism will be like a hothouse, the earth will be uninhabitable by life in another century or so? And it's not very clear, nobody really knows what's happening here, and I definitely don't have an answer to this question. But this is a very, very important. It's a question of our times, that needs to be understood. And what I'll do is, through my presentation, I hope to just have a vigorous debate. I look forward to I'll present my views here, and I look forward to all the comments and questions that you guys have. Okay. So, I like to look at climate change. When I look at climate change, I like to look at three broad pictures on three different time scales. So let's look at and please, follow the graph. Okay. And this is a time scale which shows what's happened to Earth in the last 50 million years. It's a geological time scale. And if you look at temperature change, or how Earth's average temperature has evolved over the last 50 million years, it has been gradually coming down. And from its peak around 50 million years back, this is the period when the Arctic was tropical. It was as hot, at 50 million years back. And today we have come down roughly 15 degrees centigrade. And we are in an ice age for the last 2.5 million years. In the same period, carbon dioxide, which is a predictor of temperature, it's not always causative, it's causative sometimes, but it's a good predictor of Earth's temperature, has come down. A concentration of carbon dioxide has come down from around 1600 ppm to around 200 ppm. Now this data is always used by paleoclimatologists, people who look at Earth's history to predict the future climate. And they say that, hey, carbon dioxide has come down by, let's say, roughly 3 sort of halvings, or there's 3 doublings, 200 to 1600, and temperature has gone from roughly -5, these are relative scales, to something like 10. So you double carbon dioxide, you will get a 5-degree change in temperature, Earth's mean temperature. I mean, this is an important metric. This is an important graph. This is something that's used often to generally get an estimate of how carbon dioxide is related to Earth's temperature. But more importantly, Earth's temperature is dynamic, and Earth has passed through extremes of tropical Arctic and almost equator covered with ice in its past. It has passed through these extremes. Now look at another time scale, which is more like the last 400,000 or 500,000 years. So 100 times more compressed. So we are sort of looking at just a very narrow sort of region here. And the lower graph shows here, the lower curve shows here the CO2 carbon dioxide concentrations. The middle graph shows us how the relative temperature has changed. And the top graph plots solar insolation in the month of July. And all this data is based on a Russian station in Antarctica, where they've dug up the ice and they've done all kinds of carbon and oxygen isotopes to figure out how these things have changed. And what's very interesting here is that, driven by essentially eccentricity of Earth's orbit around the sun, which changes roughly 100,000 years, and Earth's precision, how the rotation of Earth and the precision of Earth changes every 20,000 years. The Earth has been cycling and having these glacial cycles every 100,000 years. And so we get to a point where every 100,000 years, Earth, there is almost like ice in Northern America. And, not California, but I guess even right up to the border of California, US and Canada would be covered with ice and glaciers. To periods where, there is rapid thawing that occurs. And we are here. We are somewhere, and this period is called Holocene. And what is very important about Holocene, and you will always find people who do Earth system studies talk about Holocene, because there's something very, very important about Holocene, which is that if you look at all these periods, last 400,000 years, this is probably the most stable temperature that we've had in the last 11,000 years. So in a sense, human history and evolution of human civilization has been closely linked to a very, very stable Earth temperature. We don't realize how fortunate human beings were, or whatever, whether we are fortunate or we are part of this evolutionary history, that human civilization has agriculture and human civilization has evolved in a period where Earth's temperature has been very, very stable. And even though there are regional climatic changes that have occurred here, there have been many ice ages and there have been very hot periods, the overall average temperature of Earth has been within like a degree and a half. Very, very narrow window. And now, the important thing here is that, there are two sort of important narratives here that I want to point out. One is that somewhere around this time, in previous glacial cycles, we see a rapid decline in temperature and the glacial cycle sets in. We are somewhere at the edge of that. It's just important to keep in mind. This is not something that's stable. The Earth is limit cycling between these two extremes. But the other message which is very important here is that now with global warming, we have crossed the Holocene boundary. So we're actually moving in the other direction. We're heating the Earth up. And we've crossed. So if you look at the pink here roughly shows the Holocene temperature range for the last 11,000 years. And over the last 200 years, from pre-industrial times, relative to pre-industrial times, around 2017 or 2018, we have heated, the average temperature of Earth has gone above 1 degree centigrade. Now, what's this big deal about 1 degree centigrade? You say, hey, 1 degree, how does it matter? We get so much variation in temperature every day, But when you look at average temperature of Earth, that doesn't change as rapidly. It does change, but on such short time scales of 100 or 200 years, it doesn't change as rapidly. And what's also happening is that the rate of increase of this temperature is roughly 0.2 degrees per decade. So we are sitting at around 1 or 1.1 today, and we are changing at 0.2 degrees per decade. So, next, I'll talk about how this will evolve over time and what climate science says. But just important to just note that, there are models here and there's a lot of information here. I don't want to, I really didn't want to, focus on some of the details of modeling. But we are somewhere here right now and rapidly increasing. And part of this talk is how will this evolve and how do people model it and what are the political implications of that. Okay, so if you look at average temperature of Earth has increased by around 1 degree centigrade relative to pre-industrial times, which is 1850s to 1900. But that is not uniform. Oceans have not warmed as much. Oceans have a large thermal inertia. It takes time to warm them up. So even the oceans have absorbed like 90% of all the extra heat that Earth has absorbed because of global warming, their temperature has not really increased. What has really been alarming is that in the northern parts of Earth, around Arctic region and subarctic region, we are getting like almost 4 times the average increase in temperature of Earth. So we are having 3 to 4 degree average warming. And this is the warming that's happening in the winter time, and this is the warming that one sees in summertime. So just keep in mind that a 4-degree warming is an enormous amount of warming, average warming. So a lot of climatic effects are happening, and some of the climatic tipping points are being reached around the Arctic. The other thing is that temperature changes have a massive impact. Just what are the big impacts of, rising temperature? There is more evaporation of water in the oceans. So there is going to be, more flooding, more rainfall in general. But there's also going to be more droughts because, after rain has happened, it's going to get really hot. So both these effects will happen at the same time. Oceans are absorbing carbon dioxide, they're acidifying. Ice is melting, and ice will continue melting for centuries even after we stop emitting carbon dioxide, because that carbon dioxide is going to stay there for a very long time. Which means, sea levels will continue rising for centuries even if we stop emitting any carbon dioxide. And potentially sea levels could rise 30 to 50 meters, relative to where we are today, if this trend continues over centuries. More heat waves, more forest fires. So we are basically taken the Earth out of the stable Holocene period, and capitalism has driven it to a point where, we are now entering into an unstable period. Nobody knows where this journey would end. Now, what is really driving this change? And what's driving this change is global carbon dioxide and global greenhouse gas emissions. Now, carbon dioxide is the primary greenhouse gas. It's a very long-living greenhouse gas. If you release it to the atmosphere, it stays there for centuries. The other 2 greenhouse gases that are important are methane and nitrous oxide. And so if you look at methane is relatively short-lived, but it's much more potent it's 40 times more potent than carbon dioxide. And nitrous oxide is also long-lived, and it is close to 300 times more potent than carbon dioxide. But what's very important here is to just understand what's happening here. Why is this? A big factor, obviously, as we know, is use of fossil fuels. That is, for carbon dioxide emissions, and this gives relative proportions of coal, oil, and gas. Another factor is, which leads to it, is something like cement production. So cement production requires clinker formation, which uses limestone, and that's a huge factor in releasing carbon dioxide, because every time you heat limestone, and you release carbon dioxide. So limestone is also a fossil. And then land use change, deforestation is a big factor. In fact, if you look at the last century and a half to 2 centuries, land use change is probably as important a factor as coal, as far as global fossil fuels are concerned. Now, another sort of story here is that much of the initial emissions were driven by industrialization of what are now considered as the advanced capitalist economies. But in the last 20 or 30 years, Asia has overtaken in terms of emission anything that, and especially China, anything that has been done in either US or EU. And today Chinese emissions are more than EU and US combined. So this thing is not ending, it is being driven by development of emerging economies, development of capitalism in emerging economies. And we could debate whether China is socialist or capitalist, but that's not the purpose of this talk. But it's really sort of, this trend is continuing to increase as India and rest of South Asia and Southeast Asia, eventually Africa, industrialize their economies. If you look at what's the fossil fuel emission per capita in this graph, the left hand side shows annual per capita fossil fuel consumption, or in the countries shown here. The United States has the highest per capita fossil fuel emission. And the area under the box shows the total fossil fuel emission country-wise. And you could see that China's emissions in 2016 or 2018, 2017 were more than EU and US combined. It's more than EU, US and India combined. And Chinese per capita fossil fuel emissions are also at the level of EU. So a very important question here is, what will happen to this part of the world? Because this is just the first 2 billion, 2.5 billion population out of like 9 billion. How will rest of the population industrialize? Because it will, at some point or another. And will it also now go and get to the levels of emissions, per capita emissions in EU, China and US? Or will the model of industrialization be different? And these are some of the questions that I hope to address in the remaining part of the talk. Okay. Another thing that's shown here is, just as a data point, is what is the contribution of different countries to total carbon dioxide in the atmosphere, cumulative emissions from 1870 to 2016. And here you can see that US is almost 25%, EU is another 20%, China is 15%, the rest of the world is around 40%. Okay. So that said, where are we in terms of decarbonization? And this graph shows where the cost of production of electricity from different fuel sources in 2018. And one thing that is important to note here is that, driven by what has happened in the last 10 years in the global wind and solar industry, in US today, both solar and wind are among the cheapest sources of energy relative to new coal or nuclear, which is like by far the most expensive, and even cheaper than or in the same range as natural gas. So we have seen dramatic reductions in prices of both solar and wind energy in the last 10 years. As these industries have grown, and I was fortunate to be associated with this industry in the last 10 years to really see how this dynamics has worked. So this is a mitigating factor. This is a huge mitigating factor where we have unlimited sources of energy like wind and solar. They are now cheaper than, even the economic case is generally cheaper than putting new coal, or definitely nuclear. Nuclear is very expensive in US, and that alone sort of precludes nuclear. One of the reasons, people advocate for nuclear don't realize is that one of the reasons why nuclear is not getting adopted is not just opposition to nuclear, but the fact that nuclear is way too expensive. Nobody wants to put nuclear, there are cheaper sources and better sources available. Now, while in as much as solar and wind have become cheap, they are still expensive compared to existing nuclear with fully depreciated plants and existing coal in US. Existing coal in US is just a shade cheaper than, and this is one reason why as coal plants are retiring, nobody is replacing them. People were replacing coal plants with combined cycle, natural gas, and now increasingly, even in states like Texas, which are completely free for all, free market economies as far as energy is concerned, there's rapid growth of wind and solar happening there. Not combined, not natural gas. Natural gas is happening, but just driven by market economics and a little bit of mandates. We are seeing a rapid rise. But all this change is driven by retirements of old plants, because existing plants are still cheaper than we expect. And I'll talk about it, in the coming slides, that this pattern will change in the next 10 years. Now, another source of energy that is rapidly sort of, driven by Europe, but now also US and China, is offshore wind. But wind has, people hate having wind plants next to their homes. So, so getting wind energy permitted has become very difficult in US and Europe. And so people have, and developers have gone, and this technology is emerging very rapidly, offshore wind. And this is the US price of offshore wind. In Europe, offshore wind is in roughly the same price range as onshore wind. These wind plants are built on the continental shelf and are 15 to 20 miles away from the shore, so nobody can really see those wind plants. Now, people expect that in China and in Asia, this equation is slightly different, where new coal is still cheaper than wind and solar. But based on cost curves and trends, people expect that new coal and solar and wind will become cheaper than even new coal in the next 5 to 10 years, in all across Asia and Australia. So so this is a great mitigating factor, and it's it can we're going to assess, and this talk is about what will be the impact of this in terms of climate change and global warming. Another curve that I want to show here and is in US we have something called Department of Energy runs a Shunshot program, and the Shunshot program, it's for wholesale electric generation through solar power. They set up a goal of 6 cents a kilowatt hour for 2020. Now this goal was met in 2017, at 6 cents was reached in 2017. And today the average is around 4.5 cents, as I showed in the previous slide. And the goal for 2030 is 3 cents, which is like half of their goal for 2020. What's really important is that not only have solar and wind become so cheap, but technological innovations there are still driving their costs down. I expect solar in the next 30 years to become 4 to 6 times cheaper, less than 1 cent a kilowatt hour when generated in large quantities at utility scale plants. And I expect wind also to become 2 to 3 times cheaper. So this whatever we are seeing in terms of solar and wind, revolution is continuing. It's an ongoing thing. The underlying technical factors have not changed, and the cost curves are going to be driven lower and lower. Now there is a lot of questions that wind is intermittent and solar is intermittent, and you really need coal, and which is partly true, and maybe nuclear. These sources of energy are intermittent. They change over a day and over seasonally. But when averaged over large areas, these sources are not really as intermittent as we think they are. A wind plant may have fluctuations every minute, but when you add wind plants over 400 or 500 square miles, then they're pretty stable, and they don't fluctuate as much. Solar is a very valuable source of energy. Most of human activity happens in daytime. All our air conditioners are turned on during daytime, and most of the energy peaks happen during daytime, and solar generates cheap and good energy in those periods. Solar is a very valuable source of energy. People who think nuclear is better and solar is bad don't understand that solar generation maps with human consumption of energy. More than that, it takes something like 10 to 15 years to develop a nuclear plant. By the time you go from permitting and siting and understanding all the environmental issues to building a nuclear plant, it takes 10 to 15 years. You can build a solar plant in from conception to by the time you construct it, you can do it in a year and a half or 2 years. You can do rapid deployment of solar plants. So solar is a great source of energy, and now solar coupled with other techniques is gradually becoming baseload energy. In fact, solar with 4 to 6 hours of storage is already cheaper than nuclear by a factor of 2. It's like 6 cents a kilowatt hour in US. Something like concentrating solar power, and I won't talk about this technology. It's already it's cheaper than nuclear even with 12 hours of baseload power. All these things are available. Nobody wants to use storage, or because as it is, these things are so cheap, and when averaged over large areas, they are not intermittent, that nobody is using storage now. Nobody is asking for more batteries with solar. Nobody is asking for CSP with baseload power. These things are not happening. The industry is growing rapidly without even using, trying to convert solar and wind into baseload power. I'll talk about it a little more later. Now, I want to talk a little bit about batteries. Now, 5 years back, when I looked at lithium-ion battery storage, these things were so expensive, I never thought they would get adopted. Now, this is a curve, this is a forecast by Bloomberg New Energy Finance, where they have looked at how battery pack prices have changed over the last roughly 8 years, and how they're going to change over. And they forecast based on their evaluation of various trends, how these battery pack prices will evolve over the next 10 or 12 years. Now, when I started looking at battery packs for energy storage, they were around in this range. In 2014 and 2015, they were $1,000 or $1,200 a kilowatt hour. Today, these packs are less than 200, sub 200, maybe like 150 to 175. You know, Tesla and GM and all, they get their battery packs in 150 to 175 dollars a kilowatt hour. It's forecasted that by 2030, this price will drop by another 3x. And the world will have like 50 to 100 gigafactories like the ones that Tesla has built in Nevada. So there's a massive innovation and reduction in price due to scale that is happening for renewable energy, for batteries. Electric vehicles are already cheaper than internal combustion engine based cars when not on a capital cost basis, but as far as operating costs are concerned, they're already cheaper. I mean, I drive an electric vehicle. It's, you know, my fuel costs are like 1/3 or 1/4 of gasoline. But even on a capital cost basis, all the light duty vehicles, most of them are, you know, expected to get cheaper than conventional internal combustion engines by 2030. So there's a tremendous technological change that is happening at the foundations of energy and transportation in capitalism. And we have to assess what's the impact of that, and you know, and I'll touch upon those issues. So what's really happening as a consequence of this sort of massive scaling of renewable technology? Today, this graph shows share of new electricity generation capacity and share of basically renewables and new electricity generation capacity worldwide. And the red line shows what the left-hand side shows the percentage of renewables as a fraction of total new capacity that is being built worldwide. And we already sort of, renewables are like 60% of worldwide capacity. They've become so cheap that all the new capacity that is being built today and that is being added, renewables are a large fraction of that. And that's natural given the cost curves, that it is expected that in another 5 to 7 years, all new capacity will be based on renewables. There will be coal, there will be natural gas, but all incremental capacity would be based on renewables. And this includes hydro. This is solar, wind, and hydro. Now for electric vehicles, you know, light duty electric vehicles, the world sort of, you know, manufactures something like 75 million vehicles a year, 75 to 80 million vehicles a year. And this is worldwide, including US, China, Japan, Russia, Europe, South Korea, you know, some of the major points where vehicles are manufactured. And electric vehicles are a very small fraction of that. Now it's expected that in the next 20 years, half of all, this is just by the natural economics of capitalism, half of all vehicles sold will be electric vehicles. And this trend will continue increasing over the next 10 or 20 years.
So what you say, ICE is internal combustion.
ICE is internal combustion engine. If you have any questions about the acronyms here, please feel free to ask. You know, I know, I'm sorry about that. Okay, B is battery electric vehicles, PHE is hybrid electric vehicles, and this is like all electric vehicles.
Could I just get, what is PHEV?
So plug-in hybrid electric vehicle. So when you buy for example, a GM Volt is considered a plug-in electric hybrid.
Toyota Prius.
Toyota Prius is both plug-in and non-plug-in. It comes in both versions.
Okay, so the BEV is different, and so
BEV is just like Tesla or, you know, Nissan Leaf. These are all completely battery vehicles.
electric. Okay, so ICE is electric.
ICE is internal combustion engine.
So the gas or
Gas.
Gasoline.
Gas.
Sure as gas.
Gasoline. Okay, so this is gasoline.
That's how I.
This is gasoline. This is non-gasoline.
Yeah.
Okay. So what is the impact of all this? You know, this sounds all nice, but what does it mean in terms of climate change and global climate emissions? Now this graph shows, this is by McKinsey. This graph shows, and I think it's pretty representative of a lot of graphs I've seen. It shows how the mix of fuels in the power industry, power generation will evolve over the next 30 years. And black is coal, grey is gas, and you have a bit of